Asymmetric encryption plays a crucial role in cybersecurity. It provides a secure method for exchanging symmetric-based encryption keys that eventually will ensure confidentiality during communication. And we've seen this occur after the three-way handshake begins in our networking module, whereby we see the client hello and the server hello communication exchange. It's here that the asymmetric encryption is used to securely exchange a shared symmetric-based encryption key that we saw function in the previous lab. So what's the difference between the two? Well, asymmetric encryption involves generating a key pair, a public key and a private key, where the public key can encrypt data and the private key can decrypt the data, whereas symmetric is encrypted and decrypted with the same single key. Let's jump in and see how this works. First, we'll need to generate a key with the OpenSSL library again, but this time we'll be generating a private key. So there's a different statement here of gen p key for private key, and then we'll use an algorithm of RSA. The RSA algorithm, while it goes back to 1977, is generally still widely used and considered to be secure. There are more emerging types of algorithms for this type of encryption, but this will do the job to demonstrate the purposes and is more than secure. And then finally, we'll write the key to a file. Cool, the process is done. Let's see what that key looks like. You'll notice it'll look a little bit different this time. That there is the keys to our kingdom, so to speak. And did you notice that double equal sign at the end? That's base 64. And again, remember that base 64 is encoding to ensure the safe transmission of data. Because if we were to take a look at this in a moment, and we will by decoding it, you'll see it will look pretty unwieldy to work with in terms of characters. So what you're seeing here is a general format called .pem. And that is what provides that top header and the bottom header that's kind of sandwich that base 64 encoded data. .pem formatted keys like this are very widely used, and they have a lot of additional features to them, such as being able to use a passphrase to also add another layer of security to a key. Cool, well let's go ahead and take a look at that base 64 text. First, let's copy the private key to another file so we can work with it and remove those headers. We can call that something like priv key data. And then we can vim into the file and then run dd to remove the top header, shift G to get to the bottom line, dd once again, and then right quit and save the file. Okay, let's base 64 decode it now and see what it looks like. And yeah, that's what it actually looks like. Notice that little emoji inside there as well too. So you can see trying to transmit that would be very difficult. You're going to have some data loss. Something's not going to get transmitted properly. So I'm actually going to demonstrate how well base 64 encoding works by decoding that file just like we did. But then I'm going to pipe and encode it once more to sort of simulate a decode and encode process in transmission. And then we'll save that to a file, and then we'll come back to that later in the lab just to demonstrate how well it works. If we look at that PEM key, well, we can see it's there. So it's actually returned back to its original state. Even though there seems to be some weird issues with the spacing, you'll see that it's sort of overflowed a little bit in terms of the original formatting, but that's actually not going to matter. So again, I'll come back to that later in the lab, but I just wanted to show you what we're going to do initially there to get started with and then come back to later. For now, let's carry on with our original private key. Our private key actually lets us generate the matching public key pair for it. And that's why it's really important to not lose that private key. So let's write this OpenSSL statement now, and we'll specify RSA, and then tack pub out to let the statement know that we're writing out the public key somewhere. We'll then specify the private key with a tack in, and then a tack out of where the file name should be saved. Cool. So that's our public key. Let's cat it out and see what it looks like. And it's a lot less in length compared to the private key, right? And it doesn't need to be that complicated because the public key will just be used for encryption. And then we'll use the private key for decryption. All right, next we need some data. So we'll do another echo statement here. And I'll throw something in like, this is data I'm going to encrypt with the public key that can only be decrypted by the private key. And I'll put that inside of a message.txt file for us to work with. Okay, good. So now let's walk through the encryption process. I'll do a command here of open SSL, and then there is an RSA UTL, so RSA utilities, and then we'll do attack encrypt, tac pub in, tac in key, public underscore key dot pem to specify it, tac in message.txt, and then attack out encrypted underscore message.txt. And it's done. Let's cat it out and see what it looks like. And super encrypted. So this is pretty powerful. Awesome. And this will now be basically impossible to ever read without our private key. Cool. Okay, so let's do the decryption portion now. And we'll run basically the same command again, but this time we'll specify tac decrypt. And then we just need to specify all the same parameters, the in key, which is our private key in this case, so a little bit different. And then the in message being the encrypted message, and then out being the decrypted message. And if we cat this message now that we just decrypted, looking good. And so this is what happens when you're trying to connect to a website and trying to establish an HTTPS session. You'll grab their public key, and then you're going to encrypt a shared session key, which is going to be your symmetric based encryption key. And then once you send that key over, the server can use their private key to decrypt it. And then they can use the symmetric based encryption key that you sent them to encrypt messages, send it back to you, and you have the key already. So you can now use your symmetric based encryption key, which is the same one they have at this point. And both of you now can encrypt and decrypt messages back and forth on the fly. And recall back in networking when we looked at the sequence and acknowledgement numbers. That's what ensures that this little back and forth exchange is all in sequence and in the right order. Awesome. Okay, so you remember that base64 decoded and encoded private key? Well, let's demonstrate how that'll work kind of the same way when we have a message get transmitted and then it's encoded and decoded along that process. First, I need to go and get the headers from the original private key and put them inside of the decoded and encoded private key.pem. Now, you can do this with a couple shortcuts inside of Vim, YY to yank lines, Shift Z 2 times to exit without saving, and then we can hit P to append those yanked lines inside of the file. So I'm going to go back and forth and do this really quickly, and you can set this back up at the same time. Awesome. Okay, so we have the key set back up with all the original headers. Even though the spacing is a little messed up, it's still going to work just as intended because that base64 encoding and decoding process is pretty solid. So let's go ahead and just walk through all those steps again. First, we're going to generate a public key to match our very long named decoded and encoded private key. And then we're going to encrypt some data, and then we're going to decrypt some data with this new key pair, and everything is going to work just the way that it previously did. And this is just, again, to demonstrate how that weird spacing that you saw, it really isn't going to matter much. And there you have it. It worked just the same, even though that weird spacing issue was looking like it might be a little iffy. And there you have it, from last lab to this lab. Together, these two forms of encryption form the foundation of modern cybersecurity. And truthfully, it's because of this that we're able to facilitate the secure flow of information and transactions across the internet. And this makes the world's interconnected web applications and digital services that we all use every single day possible.